All right, so the 48th day of school, here we are. We're going to keep on going with linear algebra. All right, we're going to discuss some other operations on matrices, including but not limited to the concept of multiplication, as well as addition, subtraction, and an inverse, and what those mean. All right, so matrix multiplication. I think we already did matrix addition the other day, didn't we? Matrix addition? Yeah. Let's go through it. They have to be exactly the same size. Yes. In fact, let's make it not your... Okay. So the elements in one matrix map to the other element in the same position. Okay. Now, remember, these matrices have dimensions that are listed as rows and columns. So, for example, matrix A, the dimension of these, sometimes you'll see this, especially in computer science, the dimension of A would equal 2, 3, sometimes written just as 2 by 3. It's 2 rows and 3 columns. Those are equivalent. Sometimes you'll see them as an ordered pair. Sometimes they'll have, brackets or braces or whatnot, but it's got 2 rows and 3 columns. All right. So if I wanted to extract a single element, or I wanted to talk about, say, the B in that matrix, that lowercase b in matrix A, I would refer to it as being in the first row, second column. And often you'll see that written as A1, 2 equal letter B. So the first row, the second element, first row, second column, and whatever the heck is there is what I'm looking for. Okay, so that's how you can extract a single thing if you need it, or talk about a single element. If these matrices are at all different in their dimensions, they will not add or subtract. Okay, and obviously if I subtracted these two elements, then it would be A minus T and B minus R, so on and so forth. Okay, addition and subtraction rules are the same. All right, now here's where things go a little bit weird. Multiplication. All right, multiplication does not commute in the world of matrices. I'll show you. A times B is not equal to B times A. Let A and B be different matrices. I mean, the previous examples excluded from thought at the moment. And if I have two matrices, A and B, and they can multiply, they will very, very often not be commutative. There are extremely rare cases where they do commute. And those are so rare that if you're really interested in finding out about them, go get a PhD, because you could easily. You might need that level of math in order to read somebody else's PhD on what matrices commute. because they don't very often. Let's do an example. Let's deal with something small, and we'll go bigger from here. All right. When you multiply these, there are different ways of doing them, and often they rely upon heavy sigma notation and whatnot, but I find that this following visual method is the most straightforward, I hope. Give yourself a little room here. So this was matrix B, and that was matrix A. Notice where that's really ugly. Please note where they are, because if you do these in the opposite direction, they will not work the same way. And if you it's very common to goof it by not putting them in the right places. Whatever is second goes above, okay? So just kind of like write them side by side and shift the second one up, because your answer is going to show up right here. All right, that's where the resultant would go. Now, when I'm looking for this very first, the 1, 1 element, I'm going to go down this row, and down that column and across this row, and kind of like targeting, like zooming in on my target. That's where my element would go. And for example, whoops, sorry. And when I go for this element, that's where it would land, okay? Now, let me explain what I mean. Let's do the very first element. So I would go and put in that space 3 times -1. That's the first element and the first element. That's him and him. I'm going to multiply those two together. And then I'm going to add it to these two multiplying against each other. That's how it goes. It's kind of like zooming in on your target, stepping in towards it. So I get -3 plus a -12, or -12, gives me -15. That's what's going to go right here. Okay? I want to make sure that everybody understands how I got that number. Try on your own, just to see if we're all on the same page. Try and find me what goes here. You would go and use these guys and those guys, and they would land. You would obviously not fool with your 15. It would just be the 2, the 7, the 3, and the -4. It would multiply and land on that spot. Who thinks they know what it is? What do you think? That's what I got too. To get that number, he did and I did as well. 3 times 2, and then negative 4 times 7. So 6 minus 28 equaled negative 22. That's how that number was created. Come on, play nice. Who follows? Awesome. All right. So I'm just going to go ahead and shrink all that. Shrink all of that. And go ahead and try and find the other two elements. So what's my 2, 1 element? Okay. Yeah. 2 times negative 1. Thank you. And then 6 times 3. So negative 2 and 18 yields negative 16. Okay. Cool. Now for the last one, 2 and 2. Running out of room. Oh, was that? Yeah, Dane Bramage. Right. Thank you. A little arithmetic will get you every time. So 2 times 2 plus 6 times 7 yields 4 plus 42, 46. Oh, that's kind of neat. Fun with smartboards. Actually, it's a really good illustration of vectors and midpoints, but we'll go there later. Perpendicular bisectors. Oh. Okay. Good question. Let me just fix everybody so everything's working. Okay. Let's take these same two matrices, A and B, and multiply them in the opposite direction, in reverse. And we'll see what happens when things are slightly different. So now, when we multiply these, we get 3 times negative 1 plus 2 times 2, negative 3 plus 4 equals 1. Automatically, you can see that you're not getting the same answer. See? They do not fly. I mean, multiplication is not commutative anymore. So the next one would be 16. And then 9 plus 14 gives me 23. Negative 12 and 42 gives me 30. These do not commute. It is important to note. All right. Sure. Outside of using a calculator? Only in that it's the same thing as your multiplication tables in a sense. It's like, are you doing the arithmetic correctly? You kind of just need to double check your math and make sure you're not making a silly mistake like I did, dropping a negative sign or adding a negative sign or something silly. Okay. So matrices do not commute. That's the takeaway message. All right. Now, there are some restrictions on what can multiply against each other. Okay. For example, if I tried to multiply and look at what happens. Yeah, we have a problem. The 3 and the 1 would multiply, the 2 and the 3 would multiply, and then the 1 wouldn't have anybody to play with. See? Doesn't quite work. You could start by going this way, but you'd wind up not having enough playmates for all of your elements. So this doesn't quite work. However, let's see what happens if we try to do it in reverse. Does it play? It does. 1 times 3, negative 4 times 5. Okay, we wind up with negative 12.
So are the sides?
No, sorry, 20 and 17, negative 17.
So are the sides supposed to be like mirror images of each other?
Well, there's a rule to it, and we'll, in a minute, take a look at it. And I want to say that even when you get down to here, it still would, you have 1 times 1, negative 4 times 7 would be how you found all of those elements, you see? So it's a systematic way of finding the multiplication of the product of two matrices, okay? So this element would be 1 times 1 plus negative 4 times 7. So 1 minus 28, negative 27. Would go right there. All right. So we have to be able to find a way to say, hey, how do these work? Now, let's look at this. In fact, would this still fly? Does that work? Yeah. Right? I could find all of these numbers. Haven't yet broken any rules. 3, negative 20. So we wind up with negative 17. It's a lousy looking 17. 2 and negative 24. So, yeah, these multiply. Well, let's look at it. What did I have? I had what are the dimensions of this little guy on the left? the 1 by 2 row column. This is a 1 by 2. And I multiplied it by what dimension matrix? 2 rows, 3 columns. And the result is a what? A 1 by 3. What do you see? Remember, if we tried to do this in reverse, it didn't quite work, did it? This one didn't quite fly because I can do the 1 times the 3, but then the 2 and the 1 don't have any playmates. So this one didn't work. And this one was a 2 by 3 times a 1 by 2. Epic fail. All right, it didn't quite work for me. The rule, if you can see it here,
Row the first one.
these two must be the same, and these two are those two. In order for you to multiply, you have to have the same number of columns as in the first one as rows in the second one in order for it to work. So sure. All right, so here's a perfectly valid test style question. Find all of the different products. You know, who could actually multiply? Could you multiply A times B? Shrink this a little bit. If I did A times B, that would be a 2 by 2 times a 3 by 2. Would that multiply? No, the two middle numbers have to be the same. Okay, so this does not work. Oh no, there's more. B times A. B times A would be a 3 by 2 times a 2 by 2. And that would work. And it would yield a 3 by 2. Okay? The two middle numbers have to be the same. Find me some other things that will multiply. Was that a question? Sorry. You had your hand up. I thought it was a question. Sorry. What other things might multiply? C times B would work. Oh, excuse me. C times B flies. And there you're making a 4 by 3 times a 3 by 2, which would yield a 4 by 2. Okay? What other things could fly? D could multiply to C. So what we're dealing with here are permutations or combinations? Order does matter. So is that a permutation or a combination? It is a permutation. Okay, so another flashback to older material, right? So something like this might work. Now, let's say we had, just for giggles, haha. Let's find out what D times C times B times A would be. Woo! Now, this is left multiplication. Yes. It's left multiplication, yeah. There's a difference between left multiplication and right multiplication. Okay, matrices multiply to the left. Okay, it's the first guy times the second guy. In a sense, what you're saying to me is this. D is multiplying against the product of all of those. C is multiplying against the product of them. That's C, that is left multiplication, where I would first do B times A, get something. And then multiply C against it and get something else. And then multiply D against it and get my answer. You see? So B times A would produce a what size matrix? Yeah, it would be a 3 by 2. And then C multiplying against it would produce a 4 by 2. And D multiplying against that would produce a 2 by 2. So my final honest to God answer would be a 2 by 2 matrix with a whole lot of work involved. But they're all relatively small matrices. And if I keep the numbers small, that's a valid test question. Okay? Something along those lines. All right, do we see how matrices multiply? You will have problems to work on. But in fact, actually, let's try this one. Let's see how well you guys do. Make it a little bigger. I don't know. Probably, a little bit. Who knows? Try both of them. One of them does, one of them does not. All right. So there we have the basics behind matrix multiplication. All right. There are some interesting applications to this. All right. Now, all right. We talked about an augmented matrix the other day. Okay. For example, we said that this system, and I'll make one that actually works. All right. That'll work. All right. We described this system of equations with an augmented matrix. We talked about a coefficient matrix. We talked about a solution matrix. The coefficient matrix, 2, 1, 8, 3. In the solution matrix, -5, -21. All right. Well, we can describe these using matrix multiplication. For example, if I do the following, now all of a sudden I've turned two matrices into a single equation. And let's multiply this out. When I multiply these two matrices, we wind up getting, in this position, 2 times x plus 1 times y. And 8 times x plus 3 times y. You see how that works? We actually have this, what we can now begin to describe as a vector. All right. It's a vector because it is a description of motion along the x-axis and motion along the y-axis. Okay. In fact, since these are orthogonal to one another, they're at right angles to each other, right? An x and a y, and motion along the x-axis, motion along the y-axis. This is actually a basis vector. And we'll talk about that next unit. I can describe anything in a two-dimensional plane as having an x location and a y location. That's enough information for me to say where a point is. Okay? And we'll talk more about this when we go into 3D graphing and all that fun stuff. All right. Before we go any further into solving matrix equations, we have to know what a guys, calm down over there. We have to know what a 1 looks like. Okay. An identity. An identity, an identity you can think about as being an element that does not produce a net effect, okay? Given a particular operation. So multiplication by 1 in the real numbers does nothing. Doesn't change whatever you multiply it against, right? If I add, what number that when I add it to something doesn't change that? 0. So we have identities. Multiplicative identity for the reals is 1. Additive identity for the real numbers is 0. All right? There is always only one identity. You can't have two identities. Some rules for being an identity. Okay, so I'm saying A is a collection of matrices of a specific dimension. So if I wanted to talk about the 2 by 2 matrices, the 3 by 3 matrices, the 50 by 50 matrices, they're all going to be different collections of matrices. And just like we saw, the size matters when you're multiplying. I can't say that I can't multiply a 2 by 2 against a 3 by 3. It doesn't work, right? So now A times I is equal to A. I times A is equal to A. I times I equals A. I times I equals I. And just like with multiplication, if I have, say, for example, let's hop out of matrix land and go into real number land for a moment. If I have 5, and I wanted to multiply something against 5 and get 1, what would I do? I'd multiply it by 1/5, wouldn't I? Okay, so the analogy to this is that I have an element of the real numbers. And there's something out there that will make my identity. If this is A, this is A inverse. Go back to trig for a hot second. We talked about the arc sine and the arc cosine and the arctangent. On the calculator, it's the sine with a little -1 above it, right? Remember that on a calculator? You've seen those? That says, give me a number, and I'll tell you what angle it is. It kind of undoes sine. It's the inverse of sine. Okay? Inverses multiply to get the identity. So here's a small set of I shouldn't say real things, small set of matrices that actually do commute. They're very rare, but they're very useful because they allow me to destroy a matrix if I need to, or at least bring it down to the identity. What the heck does this identity look like? That's what the identity matrix looks like. That's why that one had to be the augmented. That's why you're going to the augmented matrix. If you had a 3 by 3, I should preface this. I for the 2 by 2s is not the same as I for the 3 by 3s. Et cetera, et cetera, et cetera, where we just have this diagonal going of, from top left to bottom right of ones. Okay. So let's play with this. We will do A times I. So multiply that, and you'll see what happens. Yeah, it kind of just didn't do much, did it? It went through a lot of rigmarole, but it didn't really produce anything useful, except itself. 3 times 1, 0 times -2, 4 times 1, -1 times 0, 0, -2, 0, -1. So A times I equals A. And if we do the same thing, yeah. Yeah. Wouldn't fly. The dimensions wouldn't work. Still wouldn't work. Because you'd be dealing with, here, versus a, see? Somebody wouldn't have a playmate. Not good. Now, we do this 3 and 0, 0 and 4, -2 and 0, 0 and -1. So the identity matrix will commute. It's one of the few that does. All right. Now, here's where the fun begins. Ha-ha. Let's call these things some names. Let's give these guys some names. Let's call this A. We're going to call this X, capital X. And we're going to call this B. Now what we've done is we've turned a system of equations into a very, very, very simple equation. And remember, the whole object of all of this is to get X alone, right? Find out what those are. So here's how we're going to do it. We need to get rid of the A in order for X to be alone. So what we're going to do is we're going to have to do a multiplication. Wait, hold on. See, I'm going to left multiply somebody. We'll figure out what he is in a minute. Okay? And remember, these guys commute. And what happens to here is this guy becomes I. Now, you're not going to have to do this, but you do need to understand what's happening. Okay? So let's figure out what the heck this A inverse actually is. All right. Matrices can represent a lot of stuff. And one of the things that matrices can represent are motion along the x-axis and the y-axis. They can move things in two-dimensional space. We need to first determine what this is. A determinant. The determinant of matrix M is equal to A times D minus B times C. So, for example, would equal oh, thank you. Something was sitting right with me and I didn't know what it was. Thank you. Minus 10. Thank you. Gosh, man, not enough coffee today. Good day. Thank you. Ugh. What is the determinant? Okay. The determinant is a way of saying how far away is this matrix from unity, from the identity. How messed up is my matrix? Okay. No, this doesn't really tell you anything unless you're looking at it graphically, when you're actually looking at what a matrix does to a number. But if I take a coordinate pair like this, which would be the coordinate pair 2, 1, right? And I multiply this matrix against it. It would produce 6 and 2, which gives me 8. 10 and negative 4, which gives me 6. So it took the point 2, 1 and brought it to 8, 6. Okay? It basically shifts my point to another spot on the coordinate plane. Now, if my determinant is very big, it will shift it far. If it doesn't move it very much at all, its determinant would be small. That's what the determinant does. It's a measure of how much, the original point. Okay? It's just a number that specifies a feature of the matrix itself. Okay? Now, find the determinant of, say, what did you get? 0. This matrix, matrices that have a determinant of 0 are weird. They have a special name. They're called singular. And what happens is that I wind up getting really goofy stuff. Okay? Let's, for example, try this. If I attempt to row reduce that, let's see what happens. You do it. Attempt to row reduce that. Let's see what you get. Solve them. Yeah, reduce the matrix like your homework was. Grab some. Be my guest. Something funny happens. Well, you have a 1, right? So use it to knock out the 3. What's your first action? So 3 times 2 is 6. Added to negative 6, you get 0. 3 times negative 1 times plus 3 is 0. 3 times 4 is 12, plus 2 is 14. Uh-oh. We have a problem. Does not fly, does it? No. This matrix does not have a solution. Okay? And in fact, if we were to try and play this, looking at these two equations, right? if I wanted to graph them, right? Remember, they're lines, they're linear equations. So if I wanted to graph it, that's what the first line would turn out to become. 2x minus y equals 4. Negative y equals negative 2x plus 4. Y equals 2x minus 4. And notice what happened. What did you wind up getting? If you were to graph those lines, what would you expect to see? Two parallel lines, and parallel lines do not intersect. There is no solution to this system. Okay? Singular matrices produce things that do not intersect. Okay? Now, there is a name for this, and I always mess these up, so I wrote them down. Consistent, inconsistent, dependent, independent. Remember those? I always mess up these definitions, well, these are dependent because they are basically multiples of each other. It's a scalar multiple, so these are dependent. Dependent systems do not intersect. Independent do. Well, if you think about the word, though, two lines that are independent of each other go their own way. They go in different directions. Like, for example, a, well, a child that's dependent upon its parents goes exactly in line with the parent. If you are independent of the parent, you go off in your own direction. No, you could run into them later. See them in the grocery store. What's wrong with that? And consistent. Um, no, I shouldn't. I'm gonna save this word. Um, Infinitely many. Yeah. Oh. Yes. Independent just says, hey, there's an answer. There's a number that I could plug in and get something that flies. Consistent says, I got one, meaning that there are two lines that overlap each other. So, sorry, that intersect each other. So, dependent systems are parallel. Independent systems intersect. Or lie on top of each other. And consistent systems, there's only one place where they intersect. All right. So consistent versus inconsistent are just specific designations behind independent. All right. But singular matrices produce dependent systems, ones that do not intersect. All right. You wind up with an error of some kind. Now, why did all of this matter? The whole job was to find out what the heck what is A inverse. So here's how we get it. That's the inverse. So the determinant of M is just a number. So 1 over that number is still a number. So we have some scalar multiple out in front. Because remember, the determinant was how much it knocked the point loose from its original location. So 1 over the determinant would kind of undo that and bring it back. So let's compute one. So what's the determinant of this guy? Right. 6 minus 8, which is -2. Now, to get the inverse, we just flip things around. Oh, excuse me. And often we see it written that way just because we're probably afraid of fractions. No, just because, leaving it out front usually results in a nicer, simpler thing, but it doesn't always. If everybody was a multiple of 2, I'd probably multiply it in. Okay, so that's our inverse. Now, let's use it. We had -5 and 21. So -15, +21 gives me a 7. No. No, it's brain damage. -15 plus 21 gives me 6. Oh, I'm good. And now 40 minus 42 gives me -2. And now I multiply the -1/2 onto it. Gives me -3 and 1. which is a heck of a lot nicer than row reducing sometimes. It's how to find the solution using the inverse. So, try this one. Ooh. We'll do a simple one to start. Oh, no, that's not helpful. Are we good? So, find the inverse and use the inverse to multiply against that answer, the solution matrix, and find the answer to this problem. We'll leave this for the audience. And this episode of The Bronco Show has been brought to you by the multiplication of matrices.